Hello, this is Aaron again, and I'm going to be doing uh, Friday, March 12th recitation. So this was all about circular motion, and before getting right into the problems, I wanted to do a derivation of our fundamental result that we're going to be using today, and that is circular motion acceleration for acceleration in a circle that is equal to omega squared r, where omega is our angular velocity. And it has units of angle per time or radians per time. So I guess we'll write that out like this. It's equal to rad per second. I hate to use rad here as a unit, but I don't have a better way to define it. Radians technically not really unit. We're not gonna get into it. But anyways, you think about angle per second. So omega equal to change in theta over change in time. If theta is like the angle that our um, our circle changes over time. So let's draw out a circle here. So fill the colors off. Okay, let's draw a circle. Draw a circle like this. Little snap, beautiful. And then let's change fill back on. Beautiful. Erase that little smudge. And we'll put some axes through this circle. Beautiful. Beautiful. So if this is our x and this is our y, and let's say we start like here. We start to go up. And like, so if it took us t time to go this way, then we would go an angle, then omega would tell us like how fast we're going basically around the circle. So we can parameterize this curve by some vector. Let's do this in black. So we call it r is equal to, so the x component of this r, so let me write this out right here. So if this is r, so it's got an angle theta, right? An angle theta in a time delta t. So we can write this out by saying r is equal to r times, and this circle has a radius r. Yeah, I should have said that. So this distance out is r. This is r. So r cosine omega t. And then r, so that's the x component. And the y component is going to be r sine omega t. So this is basically a way to parameterize how fast we're going around the circle. So say if omega is pi, so we go pi degrees every second, and if we go 1 second, then we'll end up all the way on the other side. If we go pi degrees in 1 second, 1 second will take us all the way to over here. Okay, so that's a way to parameterize a circle. So without getting too much detail, so if we want to take the velocity of our path around the circle, so we want to talk about the velocity that we're moving out at this distance over here. So over here, we're going to have, let's go to purple. So over here, we're going to have some velocity, which is tangent to the circle. So this is the velocity. And the velocity is what? That is just our position, change in position over change in time. So we can write that as, so we can write that as dr dt is equal to, now taking the time derivative of all these things inside. So derivative of cosine is minus sine, pull out an omega. by the chain rule. So we have omega r minus r sine omega t for calculus. Same thing over here, except no minus sign. Jump the gun. Omega r cosine omega t. Okay, if we want to find the acceleration at any given point, we'll do that in orange. So the acceleration is going to be, let's derive it first. So we get another derivative. So this would be d squared r dt squared. So this is equal to do the same thing again. So we get a no minus sign on the top term and a minus on the bottom term. So we get a minus, plus another omega squared r. So this might start to be looking familiar. So this is minus omega squared r cosine omega t minus omega squared r sine omega t. So at t equals 0, the radius is going to point out to our point right here. At the velocity at t equals 0 is going to point sine of 0, 0, cos of 0 is 1. So it's going to point something like straight up, just like we wrote. And the acceleration at t equals 0 is going to point minus cosine. So it's going to point in. We're going to get minus 1. It's going to point in. So the acceleration at each point is really going to point in at each point in the circle. So we can zoom in. We can say the acceleration is inside. So this is A. And if we go around the circle, the acceleration is always going to point in. And this is going to keep us in a circle, while the velocity is always going to point tangent to the circle. So now that we have these equations, so this was nothing but v. Running out of room here. And this is a. So if we want the absolute magnitude of a, which was what was up here, the absolute magnitude of a. So we take absolute magnitude of a. This is the square root of the squares of what's inside a. So that is, if we square this term, we'll get an omega fourth r squared times cos squared. And if we square this term, we'll get an omega fourth r squared times sine squared. So let's factor out that omega fourth r squared inside the square root. So go back here. So omega fourth r squared times, now we have cos squared omega t plus sine squared. I want to make this a little smaller. Let's resize it. Sine squared omega t. Okay. So we extend the square root all the way out. Then what's inside, cos squared plus sine squared is 1, thanks to that identity. So what we get is we take the square root of this, we get omega squared r. So that's a, it's equal to omega squared r. Beautiful. Let's put that in the box. Beautiful. Oops. Me and my square boxes. Let's see if I can do it. Beautiful. Okay, so that's good. Let's put a little, so we did that. So let's move into this problem now. So first problem, we have a rope hook up to a bucket and we're spinning it in a vertical circle. So which the radius is, we're given a radius 80 centimeters. Given a radius 80 centimeters. Bucket goes around the circle once every second. So what does that say? So we can write in here, if we go once around the circle every second, that means we're doing 2 pi radians per second. So that means omega is equal to 2 pi. So that gives us that. Beautiful. So that's a number. So that's r is equal to 80 centimeters, or what do we have? 0.8 meters. So we can just write that in. 0.8 meters inside the bucket. There's a mass of 500 grams, or 0.5, or yes, 0.5 kilograms. Again, I'm not going to plug in numbers, but we'll arrive at some formulas that you guys can plug in the numbers to if you need to, which I think all the physics will lie there. So let's draw a force diagram. So bucket goes around the circle inside the bucket. So I guess we're not going to draw a picture, but I will just kind of emphasize. I think I drew a picture up here. So we can imagine this is our frog in a bucket, and the force pulling it in, the acceleration here is what? It's the tension from the bucket, or rather, it's the force keeping the frog from falling out. It's the normal force from the bucket pushing back on the frog. So if we draw this frog's force diagram, we'll get something that looks like, man, do I attempt to draw a frog? No, we'll just go frog. I'm not bold enough. So at the top, the circle, we have our frog who's like pressed into the bucket, and that bucket is stopping him from like flying off. So we have the normal force. Well, we also have gravity first. Let's write that first. So we have force of gravity, and we have some other force, the normal force. Okay, so that's at the top. So now at the bottom, well, gravity still points down. But now the normal force is not pointing down, it's pointing up, because we're at the bottom, the base, the bucket is pressing up on the frog. So this is the normal force. Okay, so that's our force diagrams. So inside the bucket, draw force strength, the top of M is at the bottom. So the acceleration of the bucket depends on whether you're at the top or the bottom, right? Because we saw at the top, the acceleration it's always inward. The acceleration is always inward, right? But at the top, acceleration is going to be down. At the bottom, acceleration is going to be up. So I guess here we can write out top again. So top, and we know the acceleration, so it's right here. We were given it. We derived it. A is equal to omega squared r. So at the top, we have A is equal to minus omega squared r. In our coordinate system, down is negative. At the bottom, we have A is equal to omega squared r. Okay, cool. So now we have all the pieces for Newton's second law. So the next question, we're asked about apparent weight. So this is the magnitude of the normal force. It's basically like how heavy you feel, because it's related to your acceleration, not really your mass. So at the bottom, so let's derive expressions for the frog's apparent weight at the bottom, at the top of the circle. So at the top, we have. So let's write this out. So top. So we have sum of forces. So we have Fg plus Fn, and acceleration is also downwards at the top. So we can just assume Fg is gonna be negative, Fn is gonna be negative, A is gonna be negative. So we're just gonna cancel the signs. So we're gonna say Mg plus Fn. So that's Fn is equal to omega squared r. Okay, or M omega squared r. So that means we can rearrange to find Fn is equal to M omega squared r minus g, factoring out that M. So from this, we can see that if our normal force, so if our acceleration inward, which was this term, omega squared r, minus g. So we just look at these numbers. So omega was 2 pi. 2 pi is about 6. 6 squared is about 32. And r was 0.8. So our radius was 0.8. It's about 1. So it's about 30. And g is about 10. So this is going to be a positive number inward. But what this says is if omega squared, our acceleration, the magnitude of it, is greater than the magnitude of gravitational acceleration, g, then we're going to feel a positive normal force. But if it's less than g, then we're not. We're not really going to, this would say we're going to feel a negative normal force. But really what that means is we're probably not going to feel any normal force at all, and we're going to get to that. But now, and you can plug in these numbers here, but I'm not going to. Bottom. Okay, so now the bottom. Now at the bottom we had acceleration is positive. Now we have to be more careful about our signs. So at the bottom, we had Fn pointing upwards. So Fn was positive, plus, or minus rather, be careful about signs, mg is equal to omega squared r, m, omega squared r, ma. Okay, so that means, box that, so Fn is equal to m omega squared r plus g. Okay, so what this says is no matter what, our omega, no matter what our, however fast we're moving, however big our circle is, we're always going to feel something greater than g. We're always going to feel a force that's greater than gravity. So, and that kind of makes sense. If you can imagine yourself like gravity's pulling you down, if you're swinging, you're at the bottom of the bucket, like you're going to feel like you're going down. You're going to feel pressed. It's like if you're coming to the bottom of an elevator, you're going to feel pressed into the floor. Oh, let's put a line there. Beautiful. So, without plugging in numbers, I think that's, we're going to go on. We have 2 more questions. Okay. So, why doesn't the frog fall out of the bucket at the top? So let's go back to our top picture. So up here, right before the frog's getting to the top, it's like moving upwards. It's getting forced back down. It's moving upwards. It's getting forced back down, and it's moving upwards. So like if you were to like remove the top of the bucket right here, then what would if you were just going to get rid of the tension, the bucket, all of it, cut the string, whatever, your bucket, if you're like right at the top, you're going to fly off this way. So you're not going to fall out of the bucket. Your momentum is carrying you forward. And like acceleration, force is acceleration, changes your velocity. So if our velocity is pointing in this direction, if we were to, unless we were to, I can't even think of anything off the top of my head, you need a force to change velocity is my point. So that's the answer to that. So now imagine the person swinging the bucket slows down gradually. At some point, the frog will fall out of the bucket. So we're trying to find the minimum omega such that the frog will stay in the bucket, or the maximum omega before, yeah, the minimum omega such that the frog will stay in the bucket. So how can we do this? So we have these equations, and we can think about the situation. So if the frog's in the bucket, that means it's feeling a normal force. And if it's not in the bucket, that means it's free falling, which means it's not feeling a normal force, or the normal force is 0. So if we set the normal force equal to 0, let's say at our top, for the top equation, which is the only possible situation. So we set the normal force equal to 0 here. So then we can rewrite that top equation down here. So we can say mg is equal to m omega squared r. So this is the point where there's no normal force. So this is good, because this means we can solve for, and this means we can solve for omega in terms of g and r, because the m's are going to cancel. So we're going to end up with is m is equal to square root, oh, that was a gross square root of g over m. And that is the result. The hard part about this problem really is thinking about like the physical significance of not being in the bucket. Wow, I am really bad at drawing squares here. Gosh. One more attempt. We're going to leave it. I'm normally doing good with getting these on the last one, but fine. Not a square. But that's our answer. And you could plug in the numbers here. You'd find it. Find omega as a number, but I don't like numbers. All right, so we'll do this last problem and wrap it up. So here we have a highway curve. Oh, I just want to do one more derivation here. So I want to talk about omega, because here in this problem we're given velocity. We're given a v. So we need to find v. We need to find a relationship v and omega. So we can go to the top and we can say, okay, we can do the same thing here. We could say v is equal to r omega, or we could say v. I just gave away the answer. We could say v is equal to this thing, and let's take the absolute value of it, v. So we say absolute value of v is equal to, we square both sides, we pull out an omega squared r squared, which is really just r omega, and we get a cosquared plus sine squared inside. So that's the answer. V equals equal to r omega. So I want to show another way to derive this. So if we think about a circle again, so think about another circle. We think about another circle here. Okay, it has some circle with radius r. I want to draw, oops. I want to draw it like this. Man, I can't erase inside the circle. That is annoying. Some circle, radius r, and I travel some distance, or some d theta. So I move. So I go d theta. So I have some delta theta here. Delta theta of my r. And I'm interested in finding, I know what omega is, so I wrote that down. So omega is equal to change in theta over change in time. So I went some delta theta and some delta t. Then, if you remember the arc length formula, so we call this distance here s. What is this? Or we'll write delta s. So if you remember the arc length formula, so if we went around 2 pi, and I ask, how far do we travel? We went 2 pi around the circle. Well, that would be the circumference, and that's just 2 pi r. So if you go a distance delta theta, this distance here is r times delta theta. Okay, so that's the arc length formula. So then if we ask, what is velocity? Well, velocity is delta s over delta t, really, the absolute value of velocity. How far do we travel and how much time? So that's delta s. Well, delta s is r delta theta over delta t. But delta theta over delta t is just omega. So then we get left with v is equal to r omega, which is exactly what we found above. So, oops. Man, I am really bad at drawing squares today. It didn't get filled. Whatever. Forgot to turn that back on. Oh well. Well, we have that formula. So now we have our highway curve, and we're going as a radius, some velocity, and there's no friction, and we want to calculate the angle such that, well, we want to stay in a circle. So if there's no friction, how are you going to stay in a circle? Well, you need a force. You need acceleration, so you need a force. So if we have So let's say we start to tilt our highway at the point where it's going around a circle. So if we tilt it, some angle theta, then our car, so we draw our car, some dude. Hello, everybody. Okay, so he's driving. So we're gonna have gravity, pulling us down, and we're also gonna have the normal force, and the normal force is gonna point perpendicular to the surface, and that's good because if we didn't have this tilt, then normal force would just point straight up. But since we have this tilt, the normal force in our untilted coordinate system gains some component in the x direction if we don't tilt our coordinate system. So it's given by this x and this x and y components. And we get some inward force that's going to keep us on the circle. So let's say we're going around, we have our highway, and let me draw this a little bit differently. So we have our highway, and this section is really what we're concerned about. We're concerned about going around this little loop, and you have to imagine this is actually a circle, and this is a circle, and it has some radius. This is the portion of the highway. Ooh, that was the eraser. Okay, so we're going this way, but we need a force to stay in on this circle without friction, and this is how we get it. So this is looking at the rear of the car. I guess I'm looking at the front of the car. It doesn't matter, but we're not going to tilt our coordinate system. So what is the acceleration of the car in the x direction? So the x direction, which again we didn't tilt, so that's this way, is well, it's really inward. So it's really omega squared r, the absolute value. We're just going to think about absolute values. So the acceleration in the x direction is absolute value. In the y direction, well, we don't want to accelerate in the y direction. We don't want to slide up. We don't want to slide down because that means we're going to be moving. We don't want to do that. So we want to just stay in this spot right here. So our y acceleration is 0. So we write down Newton's laws in for these two equations. So if we write down Fn, I'm going to use vectors, Fn plus Fg is equal to m, and we had omega squared r. I guess we'll throw the minus sign in here just because how I drew this. Omega squared r, omega squared r, 0. Okay, so then we had, we'll just erase this for now. I'm gonna write out the forces. So then we had an Fn, Fn x component and an Fn y component. And for the gravity just points straight down, so that's easy in this coordinate system. So that's just minus mg. Beautiful. And then this is equal to what did I have before? M omega squared r 0. And it'll be minus because it's to the left. We're gonna remain with that. So Fnx. So we tilt it by some theta. Go through the same arguments about how this is theta. That's theta right there, and we can deduce that because the x-axis. So if we tilted this thing up, we tilted this up by an angle theta, then this vector got tilted this way by an angle theta, and by similarities of these triangles, this angle is theta. Because this angle was, if we tilted this way by an angle theta, this angle theta. All right, so there's probably other arguments to be made there, but I'll make that for this time. So what we really have is we have Fn, so I'll write out the x equation right now. So Fnx actually becomes Fn cosine theta, the absolute value of Fn. So we get Fn cos theta is equal to equal to minus m omega squared r. And then for the y equation, we get fn. Oh, sorry. This was sine theta. Messed up my trig. And then this was fn cos theta is equal to mg, moving that term over. So that means fn is equal to mg over cos theta. So we can plug that in to here. I'm realizing now that I don't like, well, we can keep the sign. It doesn't matter of there. So we just plug this in. So we get mg sine theta over cos theta is equal to, now I'm going to take absolute value. I'm going to get rid of the sign. So we're only interested in absolute value at this point. Omega squared r. So now sine theta over cos theta becomes tan theta. Cancel the g's, or cancel the m's, and divide through by g. So we get tan theta. And then we can plug in our identity. So we had up here that v's are omega, which means omega is equal to v over r, which implies a is equal to omega squared r, but that was v over r squared times r, which is equal to v squared over r. So now we have we have tan theta in terms of v squared over g r dividing through. And with that, we can solve for theta. So theta then equal to arc tan of v squared over g r. I'll write it like this, r g. And that is our first try. Beautiful. And that is our answer. And you can plug in these numbers. We're given velocity, you know g, and you know r. So we can find the theta, the banking angle, such that we'll have no acceleration in the x direction, or the y direction, I mean. So I did want to say one more thing. So this equation, there's a wrong way to get to an equation for Fn. And it involves tilting your coordinate system and just saying that Fn is equal to the component of gravity perpendicular. I did this actually the first time, and it's not the right way to do this. So a good check is always to think about your answer. So this is doing it the correct way. And then when you get here, you say, all right, so this is saying there's no acceleration in the y direction. So if we're moving in a circle, and let's say theta is equal to 0, all the way down, we're flat, then Fn is just mg, because cos of 0 is 1, which mg over 1 is n. And that makes sense. We're not accelerating in the y direction. Our normal force is just mg. But what about when theta goes to pi over 2? So theta comes like all the way up here, and we have like a flat wall. Like in that limit, if you want, like theta is going to get closer and closer, or cos theta is going to get closer and closer to 0 as you go to closer and closer to pi over 2 or 90 degrees. And what's going to happen is this normal force is going to like tend towards infinity. You're going to need a huge normal force to stay pinned to this wall such that you won't accelerate in the y direction. So that makes sense. It's always a good check to think about limiting cases like that. Anyway, this has been a long video, so I'm going to sign off.